Hello everyone, welcome back. And this is the last type of counting problem. And we're going to talk about another formula here, which is for combinations with repetition. All right, so here we want to say that the number of combinations with repetition with R objects from n distinct objects is this formula. Okay, now I know that before we were talking about n is the total objects and R was the boxes, and trust me, they still are. But before we actually think about what those represent, I just want to describe to you a type of problem that falls under combination with repetition. And at least for me, this is the easiest way for me to understand combinations with repetition. So if we take a look at a problem, so let's say I have 7 identical candies, and I would like to distribute them to 4 people. Now the key here is identical candies. Okay, that's the key word. So let's draw ourselves a little bit of a picture. So let's say I have 7 candies. So we'll just say these are our 7 candies. And remember, they are identical. Okay, so that means getting one candy is the same as getting another candy. Okay, so what differentiates one distribution over another is not it's not which candy you get, it's how many candies you get, right? So how many candies you get differentiates the distribution. So for example, if I separate these candies like so, right? This will give me one such distribution. So let's say this is person A, so first person, second person, third person, and fourth person, right? So everything before the first bar belongs to the first person, person A, and then person B, and then person C, and then person D, right? So this would be one such distribution. Now, with the same candies, so if I line these candies up again, I could give another distribution that is like this, right? And maybe like this, and like this. Now you'll notice that this would be different because now A gets less candies and then D gets more candies, right? So you can see that in this distribution that they're different. So you should also see that I'm still giving away 1, 1, 2, and 3, just like here I'm giving away 1, 1, 2, and 3. So that doesn't matter in the distribution. It's how many candies each person gets. Okay, so the question is, how do we answer this question? So in total, I want you to see that any picture that I draw involving these 7 circles and the 3 bars is going to be a different distribution. Okay, I'll say it again. Every picture that I draw involving these 7 circles and 3 bars will represent a different distribution. So altogether, there are going to be 10 boxes. I hope that's 10 there. So 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. So this represents 10 boxes altogether, right? So from these 10 boxes, I'm going to choose 7 of them to be circles. Okay, so 7 of them these 10 boxes choose 7 of them to be circles. And the total number of ways to do that would be 10 choose 7. Now, why is it choose? Because the order in which I pick these boxes don't matter. Right? So for example, if I choose this one, this one, this one, this one, this one, and then these 2 to be circles, right? That's 7 altogether. It doesn't matter the order in which I assign those circles, right? So 7, 10, choose 7. Now that leaves 3 boxes that I have to choose 3 of them to be bars, right? So from the 3 remaining boxes, I need to choose 3 to be bars. Okay. Now 3 choose 3 is just 1. So I'm just going to leave this out. So my ultimate answer is really 10 choose 7. Okay, so from the 10 boxes, I just choose 7 of them to be circles. Now let's take a look a little bit closer at what this equation represents. Okay, so you're already told that this is the equation. Okay, now we know where the 7 comes from because the 7 comes from the fact that we have 7 candies. Okay, so just for now, just for this question, we'll call R the candies. Okay, and in our case, R is equal to 7. Okay, so this is just our R. Okay, what about the top? Well, the top 10, the number 10, comes from the fact that we had 4 people to distribute, right? So N, in this case, represents people, the number of people, and in our case, N is equal to 4. Now, if we have 4 people, then we require 3 bars in order to separate into 4 sections. Okay, if we had 5 people, then we need 4 bars. If we have 7 people, we need 6 bars. We always need 1 less bar than person. So I want you to see this formula here. We have the 10 comes from the fact that we have 7 circles, but we also have n minus 1 bars. So we have 3 bars altogether. Okay, so I hope you can see where this comes from, right? So that where this formula comes from. So we have, again, the 7 circles and then the n minus 1 bars. Okay, and that's really all there is to tell about combinations with repetition. Anytime you are distributing identical candies to people, right, then basically that is that is a combination with repetition. Now, there's a couple things I want to point out here. Number one is I can put the bars anywhere, right? So that means if I put 2 bars next to each other, that means I'm essentially giving somebody nothing, right? So that's possible. I can give somebody nothing. So we should note that that is true. Okay, so we should keep that in mind. The second thing is we should note that identical candies is very important, because if these candies were not identical, then this technique that I'm using doesn't make sense, right? So if this candy, for example, is different from this candy, right, then I can't just separate them into bars, right? I need a better mechanism for stuff like that, right? So it has to be that these objects or these candies are identical. Okay, so if they're identical, then one thing that we can do is we can put it into a form that we recognize. So this is a composition of linear equations, and essentially asks the question: how many integer solutions are there to this problem? Okay, so how many integer solutions are there to this problem? So we have x1 plus x2 plus x3 plus x4. They have to be all integers, so they have to be all whole numbers that sum to 10. Okay, and this notation down here says that all of these variables have to be greater than or equal to 0. Okay, so they can be 0, but they can be anything greater than 0 as well. So I want you to take a quick look, because this problem is exactly the same as our last problem. So the only difference here is that the number of people that we have is 4, okay, and the number of candies that we have is 10. So notice that however many I give to person 1, person 2, person 3, and person 4, it has to sum to 10. I'm giving away all the candies, right? So it has to sum to 10. Okay, and how many people do I have? I have 4 people. I can give them anything from 0 up and above. Right? So it's basically I'm drawing all of those pictures, right, involving the bars and the circles. Okay, so this is what we call standard form. So I just want to highlight something. If this is an equal sign and this is a 0, this is called standard form. Okay, so in standard form, we are going to directly plug it into the equation. So remember that the n plus r minus 1 choose r equation, we're directly going to plug it into that equation, and so in our case, we get 4 plus 10 minus 1 choose 10. Okay, but what if it's not in standard form? So if we took a look at this problem, let's pretend the 0 is replaced by a 1. Okay, so what does that mean? Well, this notation essentially means that all of these people have to get at least 1 candy, right? So we can't give 0 then. Now, in this case, can we directly plug it into the equation? No, the answer is no, because in order to plug it into that equation, we should make the assumption that I can give nothing to someone. So in this case, what we should do is we essentially give 1 candy to each person. Okay, so we end up with, we can now turn this into 0, but now instead of 10 candies, we only have 6 candies. Okay, so again, give 1 candy to each person, and now we can give them nothing. Okay, so again, we can write down our n and our r. Now our r in this case is going to be 6. So this basically translates from our original statement into this new one. Right? So this we can transform this into this problem, and we can just solve it just as before. So we have n equals 4 and r equals 6. Okay, third variation. What if this had said something like the sum is less than 10? Okay, now there's 2 ways to go about this, right? So less than 10 basically indicates that we have 11 cases, right? So we can say x1 plus x2 plus x3 plus x4 equals 10, or equals 9, or equals 8, or equals 7. So we're solving 11 different problems, and because I said or, we're going to add everything together. Okay, so this is just straight up by cases, and we can do that. But instead of doing that, we're going to make it equal to 10, but we can also add an extra person. And here, x5 represents how many candies does the original person keep, right? So I'm the candy holder. How many candies do I keep for myself? Because essentially, the less than or equal to just means that. I'm distributing some candies to x1 through x4, but I'm keeping some. So I could give away everything, but I don't need to. So this x5 basically just makes up the difference for the less than or equal to. And again, we can do the same thing as before. Here our n is equal to 5 and our r is equal to 10. And so our equation is going to be something like this. Okay, and hopefully this gives you kind of a basis for how to work with combinations with repetition. Anytime you see a problem that you can translate into combination with repetition in this form, right, in like the x1 plus x2 plus x3, this form, then right away we can just use the equation. Okay, so from standard form, we can just use that equation. Okay, so let's do a quick last quick exercise here, and this is just how many integer solutions or non-negative solutions. So essentially non-negative means all the x's are going to be greater than or equal to 0, right, to these two equations. So notice that here I have to satisfy two equations. All right, so the first thing I'm going to do is let's solve this one first. And as we saw before, in this case there are 3 people and there are 9 candies. So right away we can plug in the if we were to follow that equation to the t, we would be 3 plus 9 minus 1, choose 9. So we would get something like this. Now, after I know that x1 plus x2 plus x3 is equal to 9, I can then replace the first 3 x's with the number 9. So essentially, we can do something like this. Right? Plus x7 is equal to 21. So that means we can have x4 plus x5 up to x7 be equal to 12. All right, so I can move this to the other side, and this would be 12. So now, again, I can solve the second problem, and now we have n is equal to 4. We have 4 people, and our r is equal to 12. So we can plug it, again, straight into that equation, and we'll get something like this. And now, in this case, we are doing this and this. Right? So we need to satisfy both parts, so we're going to multiply together, because this is an and type question. All right, so I hope that makes sense. That was a combination with repetition. I want to say one more thing and very quickly go back to one of the earlier exercises we did just to kind of finalize this whole thing. You might be wondering, well, wait a minute, why are we talking about n being people and r being candies in this case? Because all along we've been using r as objects and n as objects and r as people. Sorry, n as total objects and r as boxes, right? So why are we suddenly switching? Well, actually, we're not switching, because if we go back to, let's go back to the lottery example. Okay, that was in the last video. It's somewhere way back here. So remember this lottery, right? So in order to play the lottery, we said we have to choose 6 numbers from 1 through 49, right? So let's imagine the same lottery, but this time I can pick these numbers more than once. Right, so clearly, this is the same problem, but now we have repetition. So this is a combination without repetition, right? Why is it without repetition? Because once I choose the 2, I'm not allowed to choose 2 again. Okay, but now let's imagine that in this weird type of lottery, I'm allowed to pick the number 2 up to 6 times, right? As long as the number of numbers that I choose sum up to 6, that's all I care about. So for example, I can do something like this. This could be my lottery ticket. So 2, 2, and then 20, 20, 20, and 41. Right? So I can pick these numbers multiple times as long as I have 6 numbers altogether. Okay, so now just try to convince yourself that in fact the n is the same. I still have 49 numbers, and the r, the boxes, is still the same. Okay. With the exception, now it's a combination with repetition. So which is going to be n plus r minus 1, choose r. But where does that equation come from? So let's take a look at this problem. What if I said, what is the how many integer solutions are there to this problem where there are 49 people and I have 6 candies to give away? Well, you might say, well, our n, number of people, is 49, and number of candies is 6. So the equation is just 49 plus 6 minus 1, choose 6. And that's it. That would be the answer. But how do we relate it back to this problem? So in this case, the 49 people represents how many times do I pick each number. So for example, x1 says, how many times do I pick the number 1? x2 says, how many times do I pick the number 2? You see, in this case, the x2 variable would give me 2, right? So I picked it 2 times, right? And then x20 would be equal to 3. And then x41 would be equal to 1. But every other variable would be 0, right? So that's one case that sums to 6. And I want all the cases that sum to 6, right? So basically, I'm distributing 6 candies to 49 people, where these 49s variables represent how many times I choose that number, right, in the lottery ticket. Okay, now I hope you can kind of see how R and N relate to each other. But ultimately, for me, combination with repetition. So this one down here was a combination with repetition, right? So ultimately, a combination with repetition is, for me, a little bit easier to understand if I just think of N as people and R as candies. So it's up to you how you want to remember it, but I just want to say that, again, we haven't changed the definition of N and R. N is still the total objects, R is still the boxes. Okay. All right, so I hope that makes sense, and I've just realized that my picture is in the way, so I'm just going to drag this down and show you that that was what I was that was the example that I was giving. So 20 and 41. So we have 3 20s and then 1 41 here. Okay. All right, so I hope that's helpful. We'll do one more video just to summarize everything, but basically that kind of wraps up our counting series. So thank you for watching.